But I don't have to introduce myself again. This was very clear. So I will start to share my screen and then start with my presentation. I already gave part of this presentation at the EGU, at the side meeting at the EGU, which was also about iLEAPS. But I think it's good to repeat it here partly, and I also partly extended it to give you more information. So I work at EUMETSAT, which is the European Meteorological Satellite Organization. And EUMETSAT exists already since the 1990s independently. And it has been expanding a lot since then. So it was basically an organization that was only operating one satellite, the METISAT geostationary satellite. And with time, the amount of satellites that we operate and the amount of data that we process, I think called the 10 or 100,000 times more than then, because by then we had only one image per half hour, and now we have so many instruments. We have geostationary satellites, polar satellites, atmosphere monitoring, ice monitoring, ocean, land. Everything is now done by these satellites. So it's from a very small organization, it expanded to a big organization. More than 1,000 people work there now, and we are still getting bigger and bigger and always looking for new people to join. But I work in the climate section, and the climate section has as goal to prepare satellite data for doing climate monitoring, climate studies, climate services, and so on. And this work comprises several elements. First of all, there's this to make certain that the satellite data that we have, going back all the way to the 80s, are of good quality. Then we have the task to make from these data records essential climate variable data records, which are this level 2 data records. We do that in collaboration with others. But we are also very active internationally because we work together with other space agencies like NASA and the Indian Space Agency, I think, and Japanese, Korean, and so on and so forth. But we also work with the International Climate, so IPCC. So we try to do a lot of things, and it will all come back in my slides in one way or the other. So why are we observing the climate system? Probably this is a slide I always show. I think most people already know it. So this is the climate system of the Earth, roughly sketched. So we have clouds, we have aerosols, we have gases, we have vegetation. Sunlight comes in, sunlight is reflected, so it's a complex system with a lot of players in there, and we try to understand all these things. And with satellites, during the last 40 years, we are able to monitor several of the elements that we see in the atmosphere. So here I always put this line where we are now, and it's, of course, for CO2, it's a very easy one to monitor because it's changing so rapidly with time. But there are also information that are much more difficult to follow, like here this ozone, for example. This is the change of radiative forcing through ozone, and there you see that some things are not changing so rapidly. And so the ozone concentration in the stratosphere decreased, which is the ozone hole, and at the same time in the troposphere it increased. So you have there two different things that play a role, and they have a different effect on the climate. Clouds is also a very important one. They reflect solar lights. Depending where they are, they have a cooling or warming effect on the climate. So this is also important to monitor, but it's, as you see from this graph, we don't really see a global trend in how clouds are changing. We only, of course, locally you see trends. As some regions are getting more bright, other regions are getting less bright for several reasons. But on a global basis, it stays a bit the same. There seems to be a small trend of less cloudiness with time, but this is not very significant yet. Then the other thing is aerosols. It's also very important. More aerosols means basically that the climate is cooling. And because there is more pollution, basically that leads to a kind of cooling of the climate. But recently, due to all new measures that are being taken, the air is getting more clean in many countries. So that's a good message for the people living in cities, because cleaner air means that your life expectancy is much better. Less heart problems and lung problems and so on and so forth. But of course, it also means that we get warmer temperatures. What you see here is these peaks that are volcanic eruptions. I think this was the Pinatubo volcano that erupted in 1992 or 93, what is it? And so that created, from one day to the other, more or less, an enormous increase in aerosols in the atmosphere. They were shot very high in the atmosphere, like in the stratosphere, that is 20 or 30 kilometers high or even higher. And it takes then about 4 or 5 years before these aerosols are gone again. So during these 4 or 5 years, we had a bit cooler climate because of that. But of course, it's not. It disappears again after a short time, and that's not very helpful if you want to cool the climate. Then we have albedo, the surface albedo, which is a function. What is it? Where you see, of course, vegetation cycles in there, and so also important, because the brighter the surface gets, the cooler it gets in the end. So that is also something you want to monitor. Yeah, so there's many things, and this is only a snapshot of what we all look at, but there's many things you can monitor, and we have 40 years of data now available, and that is quite important, because during the last 40 years we see a lot of responses to climate change happening. And so we already are much longer in the industrial area, so that is already since 1900 or so, where we see a high increase of CO2 concentration. But it's only during the last 40 years that we all of a sudden see also the climate is changing. Glaciers starting to melt, temperatures are starting to increase, precipitation patterns are changing. So this is a recent development, and satellites can have been observing this. So that is a very big advantage when you work with satellite data. Of course, the other thing is satellites sample the Earth on a regular space and time grid in most cases, which is of course handy, because then you have the information globally available for every point on Earth, which is often making your scientific work more easy. But satellites are not ideal. You always have to combine it with ground-based observations to be certain that that what you are looking at is of the good quality. So we should not blindly trust satellite data. We should basically not blindly trust anything. We have to compare, intercompare, and there's a lot of efforts going on in making certain that we are really certain that we can draw conclusions from what we see. We made a lot of scientific progress on developing satellite-based data that are validated and high quality, and also can be used for long-term climate monitoring. And recently, and I think that is also what I heard from iLEAPS, there's much more progress made in combining different types of information, in situ and satellite observations, for example, or observations from different satellites. With enhanced computing capacities, we can do much more, and we can simulate things to understand why we see differences. So this is a very important, so recent development that we are seeing. Yeah, then I showed this picture. Actually, that's in the garden of UMedSat, where we build a new building. And what I want to show here, to make this, what you see here, took them I think 2 or 3 months, because it was basically developing the fundament for a small building that they put on top. And you don't see any, not so much result, but still it's a lot of work. And that is what I want to explain, that that's what we try to do. We try to rescue and recover all data. So rescuing means that we really try to dive into cupboards and try to find old tapes and bring this data back on our systems. So we are really looking for the old data. This is not easy, so it's really a lot of work to find these old data. Sometimes people who are retiring still have it, but that's one thing. And then recovering means that you have to reprocess all the data to make certain that they are of the same quality. So because what you see here in this lower graph is every block is a satellite instrument that was operated during a certain period. So these are all satellites. So these are, for example, the Japanese geostationary satellites. So they had 1, 2, 3, so many, and we have here all the Meteosat satellites, and here the American satellites. This gap needs to be filled, but we have here the Indian satellite, because what you see here is where the satellite is operated, that longitude. There's also several Indian satellites here. So we try to recover that. And once you have all these data, you have to try to make from all these different instruments a data set that is of the same quality and gives the same observation over at every place on Earth and at every time during the last 40 years. So that is a task we are deeply involved in, and the same is the case for polar orbiting satellites, which so they fly lower and they fly from pole to pole basically, and they see every object on Earth only once or twice per day. But also there we have a lot of different satellites, and they go back all the way to the 1970s, 80s, 70s even. If you, so like I said, if you just take different instruments, what I did here is, and you make a time series, and you compare it with, I think here we compared it with radiosonde data, and you look at the temperature difference, you will see kind of jumps in there. And these jumps are different things what you see. First of all, you see jumps because the satellite instrument changes. So we really try to make every instrument the same, to look the same, but still we don't manage. So you always see when a new instrument comes that all of a sudden the temperature is 1 or half a Kelvin higher or lower in this case, if you look at temperatures. So you see here these changes happening. That's one thing. The other thing is that if you take the data that were stored in the archive, they were processed with certain algorithms, but with time these algorithms changed. But they never reprocessed everything. So you see here, for example, in this date here, 1987, they started to use another algorithm. And all of a sudden, the temperatures dropped 4 degrees. So that was it. They discovered basically that it was too warm, and then they lowered it 4 degrees. So if you take the data from the archive and you just use them, you will get this kind of time series, which is kind of useless if you think of trying to find the climate signal in it. And that is what this graph shows. So the challenges, it summarizes basically the challenges that we have. So if you take the original data, you will see all these jumps. And what we try to do is first to harmonize the data, and you still see jumps. You see that? You still see jumps, but these jumps we understand because a certain instrument, every instrument is unique, and sometimes they just observe a little bit different part of the spectrum, and so they are supposed to see a little bit different temperature than the other ones. So we can explain these differences, so we know why they are there, and the model community likes the data like this, like these green lines. So they don't care about these differences as long as they understand why these differences are there. They take care of that in their model assimilation schemes. But for other groups, they would rather have a flat line like this here. What you see here, this is what we call this step we call harmonization. We try to keep the difference that we understand and remove the other ones. And homogenization is that we make everything in this whole series looks like as if it's coming from one satellite. That's what you see here. And I plotted here blue lines, but of course, if the distance between these two is very big. There is a bigger uncertainty of the measurement you provide here. So we try to provide something that is stable, but you have to realize the more the original signal deviates from the one that you try to simulate, the bigger the uncertainty is because you make assumptions. But still, so this is an example of where we did such a work for a lot of Meteosat satellites. So for 10, and what you see here is a temperature series for low, mid, and high clouds. So it's expressed in radiances. But I think the main message from this is that you see that the line is pretty flat. So you see every year you see kind of jumps in it. So that's natural, the annual cycle. But we managed to get rid of these strange jumps that we saw in this beginning. So this is a pretty convincing result, and because of this, yeah, the data are much better usable. But still, you see some issues that we are still struggling with. So where you see some small jumps, you never get it perfect. So then, once you have done that, so you made everything as good as possible, these data from the satellite, we start to build the climate data records. That is what you see here. So this is now the same picture as I had before, but then with the buildings on top. So that looks like a huge change, but these buildings were put in 1 day or 2 because they are just containers and they just put them like Lego on top of each other, and there they are. So that is just to emphasize how important it is that the input that you provide to your retrieval algorithms is of very good quality. At EUMETSAT, we have a network of SAFs, we call it, satellite application facilities, and they are run by National Meteorological Services, and they derive climate essential variable data records. We have different ones, so you see, actually, I think I go to the next slide because it gives a better summary. So we have one that is called the atmospheric composition SAF. So there, if you go to their website, you will find there are a lot of climate data records on greenhouse gases, aerosols, water vapors, all atmospheric parameters that are doable from satellites. You will find in their, that's what they are working on and providing. And they mostly cover the period 2007 till 2020. Some go back to the 1990s. Before that, it's more difficult because there were just not so many instruments available that could do it. For water vapor, we can go back to the 80s. But then we also have this one, the radio occultation SAP. That is, it's a new technology that is only available since 2001 or so, which uses GPS information. So it's quite interesting, but it derives temperature and humidity profiles of the atmosphere. And what this satellite does is they look at a GPS, actually the satellite looks at a GPS satellite, and it tries to send a signal between the two satellites, and then it can see what bending is taking place in the atmosphere. And the more wet it is, the atmosphere, the more the signal is bended in the atmosphere. And that is the way, that's the information they use to find out about the temperature and the humidity of the atmosphere at the location where this bending takes place. That's it's a very good quality in terms of the profiles, but it's not so good in terms of spatial resolution, because you have only a few, maybe 1,000 points per day or so where you have this information. But because the quality is so high, it's still extremely valuable. And in climate models, or in Eastern Relief, for example, in their reanalysis, they use this information a lot. Then here we have the climate monitoring software that do a lot of different things, so both atmospheric and land parameters. So I will show you later some examples of our Swiss partners from Switzerland who work on mountain information. So they look at land surface temperatures, for example, but there's also precipitation is done. There's also cloud information, solar radiation. So they have all data records or several data records with the main aim that they are very long, so that we can really monitor climate. Then we have the land SAF. So they do land parameters, so energy fluxes, vegetation, land cover, surface temperatures again. Then there's the hydrology SAF, which is precipitation, soil moisture, mainly. Ocean and sea ice, that is the sea surface temperature, sea ice concentration, and wind over the ocean. And these two, they only provide software, but it's also very important because this software is used to make the products that are there. Altogether, there are data records, about 220 data records published so far, and I think in the end of my presentation, I give the links where you can, the link is even here. So where you can find these data, and you can just register and download them and use them for your research. Yeah, so when I was in Vienna, I was asked to tell something about mountains. So I wanted to show this example. This of a Swiss partner who do for different stations, they monitor trends in temperature. But for that, they use satellite data. And what you see here, so you see here these circles, is then the trends that they saw during the last 30 years. So this is 0.3 Kelvin, 0.3. So for different sites in Swiss. And here you see that they compare. Oh yeah, I know. So these are the trends that they have observed during this last period. So that's actually the same with what I show here, but then how that looks when you look at it over time. Changes in land surface temperature relative to the mean of that period. So you take the mean of that is a temperature normal, the mean of the period, and then you calculate it normally every month or every day, whatever is needed. And in this way, they calculate the trend. So you see there is a trend, but it's positive, but it's not so strong. Not so easy to be completely certain whether it's significant. But this is a good example of an application in mountain areas where we try to say something about the changes that you observe. This is another example. So they also do drought monitoring in these areas, and they combine their products from different SAFs. So this is soil wetness index, soil moisture. Yes, that they observed over that area. Here they have the evapotranspiration that is derived from a complete other satellite, so from visible and infrared information. This is from the spectrometer observations derived. And you have here the land surface temperature, also from infrared information. So over these areas. So in this way, they are then monitoring these mountain areas, and you already see that, of course, here in these mountain areas, you see a lot of variation because, yeah, it's a difficult area to do. And the values are very low. And this is an example of, actually, I showed it already. Okay, yeah, so this is an example of one period in 2015 where there was a summer drought in southern and northern Switzerland. So I think it's this and this area that they are very dry in that period. And here we have a summer, another one. Yeah. So these are two examples of this drought monitoring project that they are doing, where they try to determine where there are droughts occurring. So this is it's a nice example of combining different types of information and tying it together. But you have to be very careful with it. I will come to that later, because this is about international collaboration. And I just show a lot of links here because this is all people that we collaborate with. So we have a very important is WMO, the GCOS, the Global Climate Observing System. They came with the concept of climate essential variables for the first time. And this is still, I think it's being used by many now in the research community. And we have then also coordination group for satellites, and that is working with climate. So yeah, actually, I think it is not so important to explain them also, but we are involved in many international fora to talk about how if we make data, that we try to follow the same standards everywhere, so that it makes it much better and more easy to compare all the data with each other. And using all the standards means a lot of things. So here is this example that I borrowed from a slide from an American colleague, where it's also, if you use the same standards, you can all of a sudden can compare things globally. And like wind, for example, is expressed in, at some point they express it in both four, so which was a skill everywhere accepted. So, and because of that, if you still read old journals from ships, we know more or less what wind speed was occurring over ocean when they were sailing there, because I just gave them the Beaufort number, which is still a quite good indication of the wind speed. Now we do it in meters per second, which is of course better because it's really an absolute number. But the fact that you agree with internationally to use the same standards is very, very important if you want to compare things and work together with each other. And we have been working in several projects on trying to achieve this for satellite data, and to do so, we introduced some matrices, also again together with American colleagues. And one was the system maturity matrix, and it's a boring thing for a scientist, I think, because it only defines how do you make a data record. That is, how should you make a data record? It's not asking you that you make it how good it has to be, but it just tells you if you do make a data record, you have to describe the software in documentation. You have to provide the code to the user community so that they can look at it. You have to provide metadata that follow international standards. You have to check the product on uncertainty in a standard way. You have to open it up to the public, and you have to also demonstrate that it's used. And so the higher the maturity is, the better this information is of these things when you made a data record. So it's, yeah, it's an administrative thing, but since we are an operational agency, you mentioned this is very important because this guarantees our future, that if we do it in such a way, you have an authoritative source of information that is really trusted as being as good as it can be. And that's only possible by providing transparency and showing that you really took the work serious. And so it does not help to scream that you're the best, you have to really show that you're the best. And I show this example here to show, okay, so this is one of the things you do for this maturity work is, for example, to compare your product with that of many others and to see what the differences are. And this is the result of a working group that I was chairing for 10 years or so, where all people who were doing cloud retrievals or was it 11 or 16 different groups who were doing that were coming together every 2 years to look at the results we have and then compare them with each other and try to find out why there are differences, because we all think that we are doing the best. Still, if you look at it, you see that there were differences. It's better now, but this was from 2008, and you see that some say that this image has 60% cloudiness, while others say 41% cloudiness. So you want to understand why is that? And in this case, this is often because it depends on how you define a pixel to be cloudy. Some say if 1% of the pixel is cloudy, it's cloudy, and the other ones say, yeah, but it has to be fully cloudy, and only then we call it cloudy. So it's just a miscommunication, and you can fix that. And that's what we try to do afterwards. So now you don't get this kind of products anymore, but you get a kind of probability for every pixel, and then it starts to look much more similar, because some so these pixels that are everywhere cloudy, that are 100% certain cloudy, but of course others where maybe, so here you see a lot of pixels which are also cloudy, but they are not completely cloudy, so they are partly cloudy, and so that is an uncertainty information that you start to provide with it. So that was one of the take-home messages from these kind of assessments, helping to improve what we were doing. So that is this quality characterization that you try to do. The other thing is then to what we call application performance matrix. So it is basically if you have a data set that you describe what is in there. So what is the coverage? Is it global or local? Is the level of the detail sufficient? So the spatial and the temporal sampling. So is there, for example, every hour an image, or every day, or every month? Depending on what some people want, it's called application performance. Certain people or certain applications want every day or every hour an image, and then you will see if you take a certain data record that only provides once per day an image, that you just say, okay, this data set is not useful for us because it does not meet our requirements. The uncertainty information, what is available, and what are the numbers. So how, yeah, so is the quality of the observations okay? So if the data have an extreme high uncertainty, you may also say, yeah, this is not good enough for my application, but for other ones, it may still be okay. And then also the stability is an important thing. So how does it vary in time and space? Also some quality indicator. If it's very unstable, so there's still a lot of issues in time with the product, it may not be used for climate trend analysis, for example. So that's another one. And then, okay, I show you, maybe I should not show this. I think this is, well, I can shortly say we had a project where we tried to determine all these uncertainties in a very systematic way. So we had I think the main message is what you see here is all kind of effects that influence the quality of your observations. And what in this project, what we try to do is to put a number on all these different effects to understand the total uncertainty of a measurement. And that can be either, and I think that is, it can be either a random uncertainties or random noise, which is not a problem most of the time, because if it's really a random noise, if you then make your sample bigger, so you, instead of going for take a 1 meter product, you go to a kilometer, you have the random uncertainty starts to disappear. So that is what you see here. The more data you take, the less this random uncertainty is. But you can also have systematic things. That is just for one satellite, it's always 1 degree off. So that is over the whole lifetime of the satellite, you will have that uncertainty in your data. And then you also have effects that are in between, because they are, sometimes the satellite is updated with the information, and then the uncertainty gets a bit less. But that is, it's a very structured way of looking at your data and uncertainties. Then I come to this slide, which is actually linked to the previous ones, because what I've tried here is to see what applications do we have for climate. And I should put also here mountain or urban, actually, yeah, monitoring atmosphere, ocean, land. Monitoring land is basically also what you do with mountain ECVs. So I just was reading a lot of reports to see what is done with climate data at the moment, which kind of applications do we have. Then here we have what instruments do we have. So we have instruments that measure in the visible, in infrared, we have LiDARs, radars, microwaves, there's a lot of different things. And then here is a list of ECVs. It's maybe not complete yet, but otherwise it's a number of ones that are at least important for what we do at UMETSAT. But I can make such a graph for everything. And if you, I don't know if this works, let me see. I good. Yeah. So here you can, so if you go here, you can see how, for example, aerosols is used in several applications, but it's only based on one instrument is very important for it. And for biomass, for example, I was just talking about that. So we also have two instruments, imaging radar and visible imager, but it's important as of vegetation. Biomass is very important in many applications, carbon cycle, monitoring land, but also in predictions and so. Earth's radiation budget is another one that is in the end only dependent on two satellite instruments, visible and infrared imager, but it's used in almost all applications. So the radiation balance of the Earth is very important, and so on. So that is what this plot tries to do. And I think one of the things I found striking is to see that so many cloud essential variables depend on only one instrument. So the infrared instrument is so important, and the visible one as well. So you need to be aware that sometimes you think you have different parameters, but basically you're always looking at the same information. So that is also something you need to be aware of, that you're not looking at different things. So it seems to be different, but it's basically coming from the same instrument. So that means that there's not complete independency. Okay, and then the last one, and it actually, I should have maybe put this plot afterwards, because it's called cross consistency. That was also something I ran into when I was listening to the presentations at the EGU from the iLEAPS project, because a lot of people do a lot of measurements and they combine them together, and then they try to do, for example, energy cycle or a water cycle study, which is it's of course something we want to do and we need to do. But even if every climate data record is of a superb quality, this doesn't mean that you can directly combine them together and then start to do an analysis on them, because there can be many reasons why they are not consistent with each other. One is that the definitions are not consistent. The semantic of the definitions is not consistent. And for example, like I said for the clouds, so sometimes you say if there's only 1% clouds, it's not cloudy, but still it can rain at such a place. And maybe the rain instrument has a higher resolution and it sees rain there. So if you start to combine the two with each other, you will see a place where it's not cloudy, but it's raining. That is confusing. The other thing what we actually discussed today was even more interesting, is you have a rain event happening in one pixel, but the water is flowing to the other pixel. So the pixel where you're looking at, you will not see rain. But if you look at the soil moisture product, the soil moisture will change because the water is flowing from another place. So you see also these kind of things play a role. So that you have to understand very well when you start to combine things, what you're looking at and what is the definitions of it. Is there a spatial correlation between them? So many things play a role. Of course, very simple is that the sampling needs to be as similar as possible. This is especially when you combine ground in situ observation with satellite. You have this issue, because the in situ observation is only representative often of a maybe 1 square meter or 5 square meter area, and the satellite pixel is 25 square meters. So that means that basically you did not sample, you only sampled less than a promille of the whole pixel. So to what extent is this in situ measurement representative for the whole pixel? This is, there have been many research going on that, and in some cases it is very representative, in other cases less. So this is something you need to be aware of. The other thing is, again, the uncertainties. I am always coming back. If there are inconsistencies, they need to be explained by the uncertainty. So that is also an important requirements. And how well do the involved ECVs compare statistically? So that is, okay, yeah, so you can also do a kind of consistency statistics checks, which is doing your own energy balance cycle. If you take 5 different parameters, you try to do a closure study and see whether in the end you end up more or less at the number 0, for example. If you do a water cycle, you see if you have closure. This is a check to see whether the data sets are consistent or as consistent enough. So this is another issue that you need to be aware of. These are the last slides because I think my time is also running up. So the final, well, another thing that we do is to tell what we are doing with our satellite data. And for that, we write climate use cases. And I show here, I wrote many of them, but this is just an example of one on tropospheric, on ozone, actually. Or was it? No, so let me check. Oh, no, it's not on ozone. It's tropospheric warming and stratospheric cooling. What I wanted to show. So this is on this radio occultation data, but it's the effect of greenhouse gases that we see in the atmosphere. The goal of these studies is to see, okay, what does IPCC say at the moment in terms of, we take a climate phenomenon. So IPCC says that the troposphere is warming during the last 30 years, and they are quite certain about that. And at the same time, the stratosphere is cooling. Also, the height of the troposphere is increasing. So that is the statement. And then I show in these studies with satellite data if we can see that or not. So this is just another way of looking at it. So we look at a phenomenon and then we see, can satellite data help us to answer that question? And in this case, it's a quite convincing result. Actually, this is coming from the IPCC report directly, where you see this is a latitudinal plot. So this is at the equator, the profile that you see, and this is at the South Pole, and it's the North Pole. And what you see is that here in this area, so which is basically the troposphere, more or less, because this is 5 kilometers here, so it only goes till 10. So in the tropics, the troposphere goes to 20 kilometers, and the more you go to the poles, the lower it gets. So that you see a warming there during this is during the last 20 years. And at the same time, we see in the stratosphere a cooling taking place. So this is actually confirming completely what IPCC is mentioning, what is happening in the changing climate. We have energy trapped in the troposphere, and that is what these data then show, and that is what we wanted to show in this case study. But there are also other ones on ozone and on the sea surface temperature, sea ice, and many other things. So I tried to write a whole series of those, and I think there are now 10 or so. And they're always written according to that principle. You take a climate phenomenon and then you try to explain what satellites see there. So that's the last slide. So the key message is space-based observations with good quality can support implementation of Paris Agreement, because we can monitor things, we can explain also, and so try to understand better what is happening and answering questions. And yeah, these observations can also provide information that is needed to generate mountain ECV. So I showed now examples what we are doing, but it's not focused on mountain areas or maybe also urban areas. So then sometimes you have to do a bit extra. So they are often made for global monitoring or regional monitoring, but not local monitoring. Space agencies provide long-term observations of these ECVs, and they are available free. And so you can really get these informations and download them from different side, but also from the EUMETSAT side, but we now also have this Copernicus climate data store where you find a lot of information. Then through this implementation of this, what is called architecture for climate, but it's basically what I showed with this maturity stuff. And so to check how mature the data are, to make everything comparable with each other. And by implementing this concept, EUMETSAT data are now 25% of all data records that are available now come from our space agency, but also a lot from the United States and other countries are coming. So, but that's actually quite a good result already, and many of them are used in IPCC. So we did a kind of check on how many are used there. So our data are either used indirectly because they are used in the models and as simulated data, but also through the SAFs, a lot of data are used. I think also important is so for the applications you're working on, maybe many of the data records have too coarse resolution at the moment for your application, but a lot of new missions, satellite missions are coming, and we recently got the first images of Meteosat third generation, and these satellites provide much higher spatial resolution data, also more precise information. And I think because of that, a lot of applications that were not possible in the past, so very local, has to look at very local phenomena. So what happens in the city with the health situation, or what happens in mountains, it's now much better feasible, because if you take a new Meteosat image, you have every 15 minutes a 500-meter resolution image of your of the whole of every pixel in the field of view of that satellite. So every 15 minutes, and then in quite a lot of channels. So, so you can really look at much better detail then. And from other satellites, we even get better than 500-meter resolutions now. So it is actually incredible how much that improved during the last decades. So it will also, use of these data will become more and more interesting also for applications that we did not consider in the past. And that's what I wanted to tell you. So thank you very much. And if you have questions, please.